Everyone. In this session, we will look into TLS 1.3 protocol. In the previous session, you might have looked into my TLS 1.3 protocol. In this session, we'll concentrate more on what is the difference between TLS 1.2 and 1.3, and we will also dissect TLS 1.3 protocol. By end of this session, you would be able to explain to your colleagues and friends how TLS 1.3 actually works. And the set of audiences here are like the college student might look into this video. This would be very helpful for them to understand how TLS 1.3 protocol actually works. And the second set of audiences are the, engineers who are trying to attend the interviews, uh, like the system design interviews, and they want to design a system design in which the where it is faster and and also the security is taken into the consideration. Then I would suggest them to look into this video. Disclaimer: I'm not using any of my company's code or any of my company's resource or internal information to provide this. Whatever I am trying to explain to you is only via this RFC, RFC 8446. So this is the RFC which I am reading. I have read and understood how TLS 1.3 protocol actually works. And the second set of information is I am looking into this website which clearly explains how the TLS 1.3 protocol actually works. This guy has done a very wonderful job. Uh, I was able to understand most of the stuff by looking into this website. Along with this, I concentrated on the RFC part. Now, saying that, let's quickly jump into the presentation point of view. In the TLS 1.3 protocol, basically, what is the difference between TLS 1.2 and 1.3 protocol? That is the first thing that you need to understand. The TLS 1.3 protocol is old, which was developed in 2018. It allows some of the bad practices and it allows some of the old ciphers, and TLS 1.2 is unnecessarily elaborate. Like it has some of the weakness. There were some of the vulnerabilities like Beast, Lucky 13, Free, Logjam, all those things affected TLS 1.2 protocol. So just for a difference, if someone asks like how TLS 1.3 protocol works, there would be a hello from the client, there would be a hello from the server, and then there would be a key exchange and then the change of cipher spec in the third message, and in the fourth message the selected key exchange and then the selected cipher suit would be sent back from the server to the client, and then the client will do some calculation and sends the HTTP request to the server, and it gets the HTTP response back from the server. So if this message takes like 10 milliseconds from client to the server, so 10 milliseconds, 20, 30, 40, 50, and 60 milliseconds to complete to get one response back from the server. It takes 60 milliseconds. Now, the same with the TLS 1.2, 1.3 protocol. The TLS 1.3 is also starts with the hello handshake message, but with one significant change is in the hello message itself, it sends the list of cipher suits and guesses which key agreement the server is likely to select, whether it is X2559 or whether it is DH, any key agreement that the server is likely to select, it guesses uh, and then sends that response back to the server. Now the server, the guessed information, the cipher suit, and then the hello message, it takes that and sends back the response to the client saying this is the key share, this is the certificate, verify, and then sends the finished message. Now the client checks the certificate, generates the key as it has the key share from the server, and then it sends the client finished message. And once the client finished message is sent, everything would be encrypted, and then the HTTP request comes from the client and then the server. Now if you see here, this was taking 60 milliseconds, whereas here it takes 10 milliseconds, 20, 30, and 40. So TLS 1.2 was taking 60 milliseconds, whereas TLS 1.3 completed within 40 milliseconds. That is one difference. it is faster than TLS 1.2. Now, the next important thing that I wanted to explain to you guys is there is something called as PFS. The perfect forward secrecy is not there in TLS 1.2, whereas in TLS 1.3, the perfect forward secrecy is there. It is like assume if someone gets the access to the future session, or if someone gets an access, steals this private key which is there in the server, then everything is gone, right? Like they can decrypt the data and see whatever data you are transferring. Whereas with the TLS 1.3, it supports PFS. That means it supports perfect forward secrecy. And by that, even though if they gets access to the private key, since it is using the perfect forward secrecy, the same key will not be used in the future. So that's one thing. We have a different session for we'll concentrate on that part. Along with that, there are some algorithms which TLS 1.2 was supporting, like RC4, SHA, 3DES, DES, AECBC, MD5. All those things algorithms are made in TLS 1.3 protocol. Now, this is what you can explain from a very far view. If someone asks you what is the difference between TLS 1.3 and 1.2, just tell them it is faster, less number of packet flow before the data actually gets transmitted. It supports PFS, and some of the old algorithms are removed. Now, let's try to dissect TLS 1.3 and see how TLS 1.3 actually works. This is client and this is server. So here, as usual, the client will generate a private key and then the public key. This uses X2559. It doesn't use RSA. This public key and this private key would be generated, and we call this process as client key exchange generation algorithm. Once this client key exchange algorithm is done, in the hello message, the first message what client sends is client hello message. In the client hello message, it sends the client version, it sends the client random data, it sends the session ID, which is not used, and then the random data is like 32 random data, which would be used in later on. We'll see that thing, but the client version, random, session ID, and then it sends the supported cipher suits. The list of cipher suits usually in TLS 1.2, 1.3 protocol is it either selects AES 128 GCM SHA-256, AES 256 GCM SHA-384, or it supports CHA 20 and Poly 1305. So the client version, the client random data, the session ID, the supported cipher suits, and then as I told to you, there would be a key exchange group which it would tell, hey, I support this group. I support X2559 key exchange group. I support SCP-384 group, 284, like different group. It tells to the server. These are all the four set of group, and it also shares it detects, okay, the server might use X25519. So it selects that X25519 and generates that public key, and that the public key would be shared here. Along with that, it will also send the list of signature algorithm that it uses for signing. So the client will send all this information. Now let's look into the PCAP file and do that. If you see here, I'm just selecting TLS 1.3 protocol. The first message which I want to concentrate is the client hello message. If I click on the client hello message, as I showed to you, there will be a random number which is there here. There would be a session ID which is not used in TLS 1.3 protocol, 1.2 protocol, 1.3 protocol. In TLS 1.2, this was used, whereas in TLS 1.3, it is not used. So instead, then you might ask me, Rajiv, if it is not used, why are we putting it? Instead of non-empty value in this field, it might release in middle box compatibility mode, right? Like someone might not understand. So we are disguising TLS 1.3 in the form of TLS 1.2. So that's the reason we are just putting some random number in form of TLS 1.2. So that's one thing, the session ID. And then the next important message is cipher suit, which we saw. And then the next important field in the PPT is, let's look into the PPT once again. Cipher suit is then key exchange group. So let's go into the key exchange group. Let's see where the key exchange group is. Supported group. If you see here, it has selected four groups: X2559, SCP-256R1, and SCP-384R1. So these are all the list of supported groups that client has selected. Now let's go into the PPT again. So the supported cipher list is group, and then the key exchange group we saw. Now the key share. So it predetermined X2559 as the server key. So it generated one key. It assumed that the server will use X25519, and it sends that key inside that key share. Let's see that. Supported group we have seen, and I am interested in key share. If you see here in the key share, it selected X2559, and this is the key exchange public key that it has sent. Now you might ask me, Rajiv, what if my server doesn't support X2559? The client selected X25519, but what if the server doesn't support X255? That we will look later on. But at this point of time, just assume that the client has predetermined that the server is using X2559, and it generated one public key, and it put that public key inside this key exchange algorithm. Now, that is one more thing which we looked into the PPT. And if we look into the PPT again, we looked into the exchange group, we looked into the key share, and then we will look into the signature algorithm. So this will be used. What it does is it performs the hash of that whole hello message by using the signature algorithm. So let's go to the pcap file and see whether it has any signature algorithm. Yeah, here, extension group, signature, it selected 8 algorithms: ECDSA, RSA, ECDSA, RSA, PCA. These are all the signature algorithm that has been used. Now, all this message comes to the server. Now, this message has been received to the server. Now, what the server does is the server will generate the public key and then the private key, and we call this as server key exchange generation mechanism. Now it generated a private key and then the public key, and then it sends the server hello message. In the server hello message, it sends the server version number, and then it sends the uh, server random data, and then it sends the server cipher suit. So the random data, supported cipher suit. Out of 4, it selects 1, and then from the 4 exchange group, it selects one of the exchange group. From that exchange group, it selects one of the key, that is the server key hash, and then it performs the hash of that whole value. Now let's look into this part in the pcap file. Now the client hello is done. Now we will click on to the server hello. Now very quickly, in the server handshake message, the server hello message which I am concentrating, a random number is there, session ID which won't be used. So out of 4 CFSM, I told you, right? Like it selected AES 128 GCM SHA-256. It could have either selected AES GCM 256 or Cha-Cha Poly, but it selected AES 128 GCM SHA-256. Now this is done, and the next important field is key share. In the key share, there was 4 group: X2559, SCP-256R1, and then the another one, right? Out of that, it selected this group X25519 and it sent its public key inside this message to the server, to the client. So this is the public key and this is the group that it has been selected. Now let's go to the PPT again. Now, now what has happened? It got the public key from this guy. It has the private key from this guy and it calculates the hash value based on the signature algorithm. It sends it into the HKDF. This was not there in TLS 1.2 protocol. It goes inside the HKDF. The HKDF will generate some keys, which the session keys, which would be used to communicate between the client and then the server. The server handshake keys, the server handshake IV value, the client handshake key, the client handshake IV values will be used. Okay. The same key would be received from the client. So the client will take the, his private key and then the public key and then the hash value. And then what it does is it sends inside the HKDF and then uh, it generates the server handshake key, server handshake value, client handshake key, and then the client handshake value. Once this is done, it will also send change of cipher spec. The server will send the change of cipher spec, which would be in encrypted fashion. The server certificate, which will be in encrypted way, and then the server certificate verify, which would be in encrypted way, and then the finish message. If server wants to verify the certificate, it can also request from the client, hey, give me your certificate. I need to verify. Even that can happen, but I don't want to go there. But here what happens is change cipherspec, certificate chain, which will be encrypted. You can't see server certificate verify, and then the finish message would be sent. Now let's go to the pcap file and see what happens. Hello message, change cipherspec. Hello, message is done. Key share is done. So hello is done. Change cipherspec. That is what I told to you. This should be in an encrypted fashion. You can't see what it is. And then the application data. And then even if there is a server certificate, the certificate would be encrypted and sent via this message. Now let's go one step further and see what is this. I told you, right? Let's go to the PPT and see what incorrect DHE. What does it mean? In the previous session, I told you it selects one of the exchange group. So it selected X25519 and it sends that request to the server. But assume my server doesn't support X2559. Instead of that, it supports SCP-256R1 or 395R1 from a different curve. Then what happens is, this I have copied from the RFC. If a client has not support sufficient key share extension, the server corrects the mismatch with the hello retry request. What I'm trying to say is, first the client, it sends the key share, it received the key share, but it was incorrect. Then what server will do is it will send a hello retry request to the client. Then the client will identify, oh, this guy doesn't support this, so I need to change. So he, instead of ECDHE, he moves to a DHE, key exchange key share algorithm. Now it selects the client and then the key share. It sends that message. Again, the same process, server hello, key share, certificate encrypted, send request, and then the application data encrypted. It verifies the certificate and then the application data flows. So there is a concept of hello retry message in TLS 1.3, which is not there in TLS 1.2 protocol. Now, the next important thing that I wanted to explain to you guys is there is a concept called as PSK and PSK with DH, with ECDH algorithm, which is present inside, which is there in TLS 1.3 protocol, which I wanted to spend some time. So what basically happens is when this message has done from the client and then the server, the client will send two extra ticket, session ticket. Once the finish message is done, it will also send two session tickets to the client. It's like PSK identity and then the lifetime of the ticket. So once what happens is in the client hello message key share, it sends the key share server certificate application data certificate verify and then it is done. Now what happens is there might be a pre-shared key which would have been shared by the client before itself. So here what happens, a client first it won't do all this operation. So initially the first message what client will do is the client will put a pre-shared key in its message. So it is like this. Let's try to draw and understand. Even though if it takes more time, I don't care, but this needs to be understood very clearly. A client and server. So first the client will send a packet to the server. So here what it does is it sends a pre-shared key which the client would have previously shared, the pre-shared key, and along with that pre-shared key, it will also share the to share this pre-shared key, what is the exchange mode that it uses, whether it uses ECDHA or anything, and then it sends a key share if to as a fallback mechanism. Now the server will receive this. Now the server will select the PSK, and once the server will select the PSK, as the server is authenticating via PSK, it doesn't send a certificate or certificate verify message. When a client offers resumption via PSK, it should also supply a key share extension. So if I told like previously, once the connection happened, it shared the ticket, the PSK. The client took the ticket. It sent the P shared key to the server. The server identified, okay, this is the PSK which has been sent the list of PSK, right? The server selects one of the PSK. Along with this PSK, what RFC says is the server responds the pre-shared extension to negotiate the use of PSK key and can respond with a key share extension to do ECDHA key extension, thus responding the forward secrecy. What I'm trying to say is as server is authenticating via PSK, it does not need to send the certificate or verify. So if you look here in my client message, there should be a concept called as PSK. So this is the PSK exchange mode and it would have shared a pre-shared key. So the pre-shared key and then the pre-exchange mode has been sent to the server. Now the server will receive, okay, this is the key. I will use that key. Instead of serving the handshake, let's start sending the traffic. That is what this is meant. So it should supply and key share extension to the full if needed. The server will respond with the preset key to negotiate the PSK establishment. There is one more concept called as zero round trip. This is a very interesting topic. So let's take in a client hello message, the client hello message. In the hello message itself, it starts sending the application data. Whereas in the previous hello message, there was PSK. This was the client key share. There was no PSK. But the subsequent handshake, there is client, there is hello, there is PSK. But in the zero round trip, early data, key share, PSK, and then the application data. Oh, that means the PSK is already there. This represents a zero round trip. It is very fast. Okay, early data is already sent in the first message. The server will check. It's like this. Let's draw and understand. Client, server. So the first packet, in this it will send the list of PSK. Along with that, the mode what it uses for the PSK. And then along with that, it sends key share. Along with that, it sends some early data indication that it is an early data. Along with that, it sends application data. In the first data itself, no hello, nothing. Now, what server will do? Server will respond the PSK and perfect forward to support provided perfect forward secrecy. Along with that, the encrypted data and the MAC of the entire message. Then tells the client will send, I am done with the early data, and then it starts sending the message. So why am I spending more time here is you might get confused when it goes to zero RTT, when it goes to PSK mode, when it goes to the normal mode. Even in normal mode, one handshake was removed. In PSK mode, there was no change cipher step. So in the handshake itself, it shared its PSK. It one of the ticket. From the ticket, it identified, oh, this guy has already made a connection. Let's use that PSK ticket and make a connection. In the third thing what it did was it used the PSK. Along with that, it also showed the pre-shared data. So here it is zero round trip. The data is started flowing from the first message itself. So it's more faster. Uh, so this will give you a very far idea. I know it's a very complex topic, but please see this video and read RFC. You will be able to understand most of the TLS 1.3 protocol. Seeing this, I will end the session. Thank you.